Okay, so I'm going to spend some time. Okay. All right, you'll have to excuse my voice. I'm trying to hang in here. All right, so a little bit more on gravitational field. I got one more thing to sort of one major topic before we have our test on friction, which I will start tomorrow. Actually, we're going to do a lab tomorrow. And then we'll start into friction. Today's Tuesday, so we'll start friction Thursday. So we're talking Thursday, Friday. So we're probably looking at a test mid to the end of next week. Okay, so just so you know. All right, so I need to give you some more stuff here about gravitational fields, some more theory. I need you guys to just chill and listen. That's all you got to do. The Earth pulls on the moon, it says. We regard this as action at a distance. Now that's a word that I'm going to expect you to understand, or a term, a phrase. Action at a distance. It's that whole idea of, can I pull the marker to me using my Jedi powers? And the answer is no. For me to pull the marker that's sitting on the table, I actually have to, okay, Junior, put it away and pay attention. Seriously. You guys got to start learning how to be students. Some of you are not students. For me to actually apply a force to the marker, I have to actually be in contact with it. You don't need to be a teacher, you need to be a student. Oh. I don't want you to be a teacher. So, action. Okay, Brad, enough, please. Action at a distance.
See, the door's not locked, it's been in your line. You know what? Oh,
Zach is not.
Mr. Reddick, can the five of us go one way or another?
I don't know. Then where do I go?
Yeah.
With them and just leave them?
Yeah, regular shotgun.
I am getting kind of tired of this. You guys are just sitting around basically having a big visit in front of me. It's kind of disrespectful. Kind of hoping that's one thing you might learn here. Because the boss ain't going to put up with it. The Earth pulls on the moon. And we regard this as action at a distance. Because the moon is being pulled by the Earth, but there's no contact. There's no rope, there's no string, there's no wire. It's a force, but at a distance, right? Because the Earth and the moon interact with each other, even though they are not in contact. Or we can look at this in a different way. We can regard the moon as interacting with the gravitational field of the Earth. And this whole idea of a gravitational field is something I've talked about, and I'm kind of coming back to it in case you didn't quite get it the first time. Kind of a reteaching, if you will. The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced into this region will experience a force. Any mass, any object that comes within the Earth's gravitational field will have a force applied to it, right? This alteration of space is the gravitational field. Now, it's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the masses of the Earth and other planets or stars that are the source of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. And so what they're saying here is, okay, here's our rocket ship, and it's moving, but is it touching the Earth? No, but we would say that it is in contact with the Earth's gravitational field. Now, does this field exist? Yes. Can you put on special field glasses and see it? No. It's just a way, a model, if you will. If you go back to that first week of physics, it's a way for us to understand something that we can't really see. We can't come up with a way to say, well, how does the Earth apply force to this rocket ship when it can't touch it? And so the way we describe it with using this model is that the rocket ship is touching the Earth's gravitational field. So this field concept sort of helps us to explain what's going on. Got that, Jeff?
Yeah.
Don't worry, man. There's nothing going on.
Okay.
You're fine. A gravitational field is an example of a force field. For something in the space experiences a force due to the field. Another force field you may be familiar with is A magnetic field, and maybe we might get to that unit. You've probably seen iron filings lined up in patterns around a magnet. If you want to look here, here's a picture of it, right? You've probably seen that maybe in elementary school. The pattern of the filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. Where the iron filings are the closest together, the field is strongest. So there's that idea again. When the field lines are close together, the field is strongest. Why did I repeat that? So, where is a magnetic field strongest? What do we call these? The poles. They exist on the Earth, the North Pole, the South Pole, the magnetic poles. Right? You don't have that picture, do you? That's okay. Yeah, that's exactly what it is. That's exactly what that is, right?
Is that why the Earth is spinning?
No. No. The pattern of the Earth's gravitational field can be represented by field lines as well. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. Now, the Earth's gravitational field is different than a magnet. Is there a pole? No. Gravitational pole. Are you with us there, Brett? Is there a gravitational pole?
No.
No. Where are these field lines the strongest? Now, when I transferred this over, some of these lines got missing, but you can see that they are over here. Again, where are they stronger? Closer together. So it's strong, and I realize you can barely read that. That's true. Strong near the surface of the Earth. Farther away it is weaker. It follows the inverse square law. Anybody watch Better Call Saul?
Yeah.
The inverse square law came up in last week's episode. Yep. I understood what they were talking about.
You're so pumped.
I was like, yeah, inverse square law. At each point on the field line, the direction of the field at that point is along the line. Arrows show the field direction. A particle, astronaut, spaceship, or any mass in the vicinity of that Earth will be accelerated in the direction of the field line at that location. The strength of the Earth's gravitational field, like the strength of its force on object, follows, there it is, the inverse square law. Now, what the heck is this inverse square law? Strongest near the Earth's surface and weakens with increasing distance from the Earth. What the inverse square law means is this. If you're 2 times 2x as far, the strength, no, inverse square, twice as far, 1 over 2 squared, 1/4 the strength. 1/4, inverse squared. If you're 3 times as far, the strength would be equal to 1/9. How do we get 1/9? 1 over 3 squared.
Or 3
4 times as far? 1 over 4 squared? 1/16. Now you might say, what does that have to do with Better Call Saul? You know Chuck, I don't know if you guys know the storyline. Chuck is the older guy. He's got an allergy to electricity. And he says in court that it follows the inverse square law. Because they say that, oh, the exit sign is on, is that not bothering you? He says, well, I'm far enough away, it follows the inverse square law. So in other words, if there were, let's say the clock has electricity in it, right? And so if I'm about here where Mika is, and it's a certain strength, okay, this distance, what would you say that distance is there? Maybe 4 meters? Right? We'll say roughly 4. Then if I go over here, I'm roughly 8 meters away, right? Well, it's not half the strength, it's 1/4, right? Much less, only 25%. And if I go over here, if I go 4 more meters, now I'm 3 times as far, now it's 1/16. 3 times, yeah, 1/9. 3 times, 1/9. Okay, makes sense? Inverse square law?
Wait, is it 2x or x squared?
2 times as far, 1/4 the strength. 3 times as far, 1/9. 4 times as far, 1/16. Okay, now, here's the interesting part. The gravitational field of the Earth exists inside the Earth as well as outside, right? Earth's gravity exists here on Earth, but if you dig a hole, it's not like gravity disappears, right? There's still gravity. I know, hard to believe. Well, think about it. Just dig a little hole, you're still in it, right? And every time you dig, you're getting closer and closer to the core. So what happens to the gravity as you're getting closer and closer? Don't you get stronger and stronger? So as you're getting closer and closer to the center of the Earth, do you get stronger and stronger gravitational field?
Yeah. Yeah.
Well, let's just talk about this.
Oh, it's like a little.
Okay, so here's sort of a thought experiment. To investigate the field beneath the surface, imagine a hole drilled completely through the Earth. We'll say from the North Pole to the South Pole. So like go to like your Bugs Bunny kind of cartoon land. Yeah, forget about impracticalities such as lava, high temperatures, lack of bathrooms, no concession stand, that kind of stuff. Consider the kind of motion you would undergo if you fell into such a hole. So, before you read on, imagine we've dug a hole right here in Dauphin all the way through. Where did we come out, by the way? Well, about 70% of the world's, everyone thinks China, about 70% of the world is covered in ocean, so you got about a 70% chance of getting wet. So North America right there, so it would be like
Ocean. Which ocean? You know?
right. I hope you can swim.
You mean China?
Yeah, we better be able to.
Especially when you consider that almost all of the landmass of the Earth is actually above the equator. So if you're in the northern hemisphere, good chance of getting wet.
Hey, what about?
Anyways, the majority of the landmass. Brazil is one of the largest. So, okay, don't lose focus.
We go to China.
Yeah, you guys go to China. Actually.
Yeah, there you go.
If you started at the North Pole end, you'd fall and gain speed all the way down to the center, provided that there was no terminal velocity, right? You would go faster and faster and faster, and what would happen at the center of the Earth?
Oh, wouldn't it feel like you're just hitting something?
Would you get stuck there?
Well, yeah, you know how important it is. How they always like.
Cartoons in it.
Okay.
Okay.
It doesn't feel like you're
Yeah.
What would happen? Would you just like go down center and you just float there?
No.
Way.
You are right about that. You're only partially right.
It wouldn't stop.
But when you get to the center, if no, because you're already moving.
So you're gonna.
If you jump in and you fall down the hole, you're going faster and faster and faster and faster and faster and faster and faster. And when you get to the center, you just stop going faster. In fact, you actually when you get to the center, you stop accelerating. But then you're going so fast that you actually go up on the other side. And in fact, if I jumped in feet first and fell all the way through, there'd be some kid in Australia, I realize it doesn't make sense, but there'd be some kid in Australia and some puncher there, and whoop, up Mr. Bennett would pop, except I'd be upside down.
Oh,
If you fall,
Would I just stop then? Well, Johnny, if I pop out of the hole, the only way for me to go, no, in fact, I would be slowing down. I'd be slowing down the whole way up, if you will, and I would just come up, assuming the Earth is a perfect sphere. Now, how could I stay in Australia?
you have to grab.
I'd have to grab hold or step to the side. Exactly. Otherwise, I'd go right back down. And I pop up here in Canada, right side up,
Dude, that'd be fun.
with a wave, and then
Really?
It'd be like tunnel something in the earth.
Dude.
Yeah, right side.
Oh, yeah.
And then-
Hey?
You don't jump like.
Swimming in Australia. through air.
If you just go in the middle.
Okay, so now Junior's question is, Junior's question is, I think, what he's saying is, what if they had a ladder that allowed me to go all the way down to the center, and then I jumped off? Then, Zane, I would just float down. How come? Because that's where, now why, I thought, hold on here, I thought at the center of this field, it would be, let me go back here, I thought at the center of this field, all the lines would be like infinitely close together, and it would be like really super strong gravity.
Yeah.
But you'd be there, so you wouldn't be getting pulled there.
Sort of, but think of what's causing the gravity. It's actual mass. So if you're right at the center, what's all around you? And you're actually being pulled outward in every direction. Because you're attracted to the earth above you, beside you, below you. You're attracted to all around, right? You'd be ripped apart.
Thank God my cat goes.
Okay, so once the set off supposed to
Yeah, I'm trying to hear Zane.
If you just like jump through, would it make more sense if you just like jump through, he's like, and you came on the other side and you just started going like up? Because you're still moving, right?
But if it's a perfect sphere, how fast am I going when I step in the hole? No. When I step in the hole, I'm doing 0. And I speed up on the way down. On the other side,
even out, you get 0 on the other side.
now, Cole's right. If I jumped off a big tall building, say 300 meters in the air, and I somehow managed to hit the hole, and then on the other side there was no big giant building, I just was a hole, I'd go 300 meters in the air.
Went straight back through again.
Not gonna try it. Wear a helmet.
How does terminal
Wear a helmet. Okay, well, terminal velocity. If you were to try this, terminal velocity was considered. You jump in the hole. After about 2 or 3 miles, you'd be going to terminal velocity. You wouldn't go any faster, and you wouldn't even make it like you would barely make it past the center of the earth.
If there wasn't me.
Because you're not, the only way to get to the other side is you have to be going faster, faster, faster. So you have enough speed that when you start slowing down, right? When you get to the center, you're
You
going to
make
start.
it a couple miles past.
Yeah.
Oh, okay.
Yes,
Assuming that you didn't burn nothing.
Yes. Whole thing is.
There's a lot of what ifs.
So I
Yeah, go ahead.
Someone should try this.
Someone should try that.
Someone's gonna die.
I'll chip in, Zane. I'll give you $5.
I'll honestly, know forever.
Well, that's true.
How are you gonna dig through earth?
Hey, remember that kid who tried to jump through the sun and jumped through all over the earth? That guy's a legend.
He does travel.
You don't speak dead, so.
All right. I got a few more things to cover here. This has been good. Some good questions. Okay. I think I've covered everything in here. If you wouldn't mind just letting me go through it, making sure that I have covered everything. Because you kind of asked me questions that I know are answered. Okay, so I've kind of done it a little bit differently. So, if you start at the North Pole end, you'd fall and gain speed all the way down to the center, and then overshoot and lose speed all the way up to the South Pole. You'd gain speed moving toward the center. Yeah, I know. I just want to go through it to make sure I covered everything. Okay? You gain speed moving toward the center, lose speed moving away. Without air drag, the one-way trip would take nearly 45 minutes to fall all the way through. If you failed to grab the edge, you'd fall back towards center, overshoot, return to the North Pole in the same time. So there and back would be 90 minutes. Oddly enough, to go all the way around, guess what? Satellites take about 90 minutes. It's the same amount of time. How come? Because the acceleration is the same. Repeat this trip with an accelerometer of some kind.
But isn't it take longer to go all the way around?
Let me finish. You're going faster, that's all. You're going farther, but faster. Your acceleration at the beginning of the fall is g. But here's one more thing that I haven't talked about. Just let me go through this, you guys. You'd find it progressively less as you continue toward the center of the Earth. Now, hold on. I thought as you got more towards the center, gravitational field is stronger. It should be greater than 9.8, but that's not true. Why would it be less? Because as you're being pulled downward toward the center, you're also being pulled upward by part of the Earth that is above you. So when you're like a quarter of the way right there, not only are you being pulled down by all the Earth down below, but you're also being pulled in every other direction. So gravity would actually be less than 9.8. In fact, right there, it's about g divided by 2. And the acceleration at the center is about 0. And Zane is right. You would float, but only if you jumped off the ladder there. Right? You are pulled in every direction equally, so the net force on you is 0. There is no acceleration as you whiz with maximum speed past the center of the Earth. The gravitational field at the Earth at its center is 0. Interestingly enough, you would gain acceleration during the first few kilometers beneath the Earth's surface. Because the density of surface material is much less than the condensed center, the mass of Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material. So because the Earth has different densities, it's kind of, there's another sort of factor there. This means you'd weigh slightly more for the first few kilometers beneath your surface. Further in, your weight would decrease and would diminish to 0 at the Earth's center. And you can actually, there's this link here, right here, takes you to, that hasn't worked for me for years. I'll click on it again. And basically it's a big map of the Earth, and you try to dig where you are. Right? If you start digging right about there, and if you can just make out there's Riding Mountain National Park, and you start digging, and then it's supposed to show you on the other side where you come out, but it hasn't worked for years. See, it didn't come out. Yeah, but you can see on the globe. Should we bother with the clickers?
Yeah. No.
I only got 2 questions. Let's just do it this way. So, if you stepped into a hole through the center of the Earth, made no attempt to grab the edges at either end, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side?
No.
Would you fall all the way through, speeding up the entire time and stop when you reach the other side?
No.
Would you oscillate back and forth with a changing speed, known as simple harmonic motion?
Yeah. Big word, so yeah.
Would you oscillate back and forth with a constant speed? The answer is C. You would oscillate back and forth. Oscillate means to go back and forth. That's what it means. With a changing speed. And that would be known as simple harmonic motion. Do you have an answer on your page? I don't think you do. You would oscillate back and forth in what is called simple harmonic motion. Each round trip would take nearly 90 minutes. Interestingly enough, we will see in the next chapter that an Earth satellite in close orbit about the Earth also takes the same 90 minutes to make a round trip. This is no coincidence. Can't remember what this link here is. Is it a video? No, it's the same thing. It's the same little guy here. Or is it a video? I seem to remember. No.
See the hole there.
All right. My voice is almost... Oh, let's do this one here, and then we'll quit. Halfway to the center of the Earth, would you weigh more or weigh less than you weigh at the surface?
Less.
Halfway to the center. You would weigh less? How come?
Halfway to the center.
Halfway to the center.
Yeah, extra less.
You weigh G over
Exactly. You would weigh less because the part of the Earth's mass that pulls you down... Did you read that on there? Do you have it? Well, at least you're paying attention. Is counteracted by the mass above you that pulls you up. If the Earth were of uniform density, halfway to the center, your weight would be exactly half your surface weight. Blah, 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 blah. Okay. I think, because of my voice, I'm going to stop there. If you want, there's more reading there on weight and weightlessness. It's basically what I went through that last lesson on weight weightless. If you're having trouble understanding that, I would encourage you to read it. I might actually have a video of this at the end. I can't remember. But my voice is done. Oh, yes.
I was back there waiting because you're waiting and stuff. So I was thinking, oh, is she gonna bet like far away? So I was so far away. No.
I have one little video to show you here.
Just grab shatter, like how big something is. Like,
Yeah.
Like the object is acting on them.
Hey?
Like the object that's acting on them.
Yeah? The bigger the mass, the greater the gravitational pull. Actually, no. They're opposed to different movements.
On March 18, 1965, Russian cosmonaut Alexei Leonov became the first human to float in space. Not to be outdone, the United States sent astronaut Ed White into outer space just 3 months later. He floated for 20 minutes and loved every bit of it. Floating around is fun and easy. The next American had to do more than just float. Gene Cernan would try to find out if humans could do work in outer space. I was going to go on, and I was going to have to do legitimate work. I had to basically assemble a whole flying backpack outside the spacecraft in zero gravity through a nighttime cycle where I had little or no light. Cernan was supplied oxygen from an umbilical hose that passed through an open hatch. His commander, Tom Stafford, seated inside, piloted the spacecraft. Cernan quickly discovered that handling even simple objects was extremely difficult. Every time I push or turn a valve,
How come?
Because he's weightless and small.
You know the answer. They knew the answer too. NASA scientists didn't think of this. Hard to believe, actually.
No, because if you're gonna
Every time he'd push or turn a valve,
it
would turn my entire body in zero gravity. I had nothing to hold on to. And we take for granted gravity because we can do that kind of work with ease if something is holding our feet to the ground. Nothing was holding me anyway. Within minutes, Cernan was sweating from the extreme effort it took to control his movements.
Within a few minutes, he fogged over. Peterson and I really ended up putting deep fog on our visor like you do when you go snorkeling or scuba diving. And so he was huffing and puffing, and I was flying the spacecraft. He says, Tom, I've got a hard time controlling myself.
And it was a very, in retrospect, somewhat of a hair-raising thing, and there were probably times where there were people down here on Earth wondered whether I'd get back in because my heart rate was running at 170 beats a minute.
So this is not a good situation at all. So I called the ground contract, said, I'll call it quits. I'm going to get him back in before we go into next night time. Got him.
why were they going back into another nighttime?
Going around the world.
Because he's going around the Earth and the sun's on the other side, right? So yeah, every probably 45 minutes he was in nighttime.
Got him in. Finally, he just couldn't hardly move. And when he opened his visor, he was absolutely pink, like he'd been in the sun about an hour too long. The next day we landed, flew the suit right back to Houston. They had over a pound or a pound and a half of water out of each boot. But he lost, I think, 10 and a half pounds in 2 hours and 5 minutes outside.
NASA was now determined to find out what went wrong.
As engineers, we started saying, look, we've had 3 missions where the EVAs didn't go well. What was wrong? Then we had a science advisory team step in and say, look, your entire principles of EVA are wrong. How you train, how you prepare the crew. Everybody forgot Newton's third law of motion. To every action, there's an opposite equal reaction. And when they touched the spacecraft repelled them.
Although weight is reduced in outer space, the mass of an object is unchanged. To move a mass, force must be applied. Newton's third law predicts an equal but opposite reaction. On Earth, gravity would allow Cernan to gain a footing and counteract the reactive force. But in outer space, the reactive force sent him reeling. Having learned the difficult lesson, NASA's next capsule was built with special handholds and footholds to anchor the astronaut in place. Most importantly, NASA began training astronauts underwater, the closest environment on Earth to weightlessness. The new training and tools made a big difference for Buzz Aldrin, the next American astronaut to do work in outer space.
I felt that it was a piece of cake outside, just moving very slowly. There was no challenge. You decide that you're going to move in a certain way and you need leverage, so you just don't allow yourself to get out of position.
It's not just as simple as just sort of going out there and doing stuff.
Go do stuff in space.
That one? Doesn't want to dig anymore for me. I keep trying every year.
Just start digging yourself.
I did dig. I click there, and I say, start digging. It's got something to do with a update or something. It just doesn't want to work. I've tried. I don't even know why I put that link in there anymore.
Just start digging. Get a tie, shovel, and start. Right there.